Hey, it's me, Destin. Welcome back to Smarter Every Day. This is the 300th episode, which is cool. Thank you so much for watching. I was on the internet the other day. I was just scrolling on my phone. I was probably wasting too much time. But I came across this amazing animation that blew my mind. It's a motor that appears to be made out of molecules. And I'm a mechanical engineer. When I saw this thing, I was like, that's a motor. Like, that's a spinny thing that has a power source. It has an axle of some sort, and it is moving. Furthermore, this one, I have a little switch here, can reverse directions, which is amazing. So I thought, I've got to get to the bottom of this because the implications for a biomechanical motor are insane. Now, specifically, the thing this is called a flagellar motor. You may have heard of the flagellum on the back of sperm or on bacteria. That's what this is. A flagellum is that whippy thing in the single cellular organism that helps provide locomotion, but I've never thought about that thing has to spin, which means it has to have like a shaft it rotates around. It's just, the implications are wild. So the more I got to reading about this flagellar motor, is what it's called, the more I realized this is a really big topic, not only in biomechanics and things like that, but in philosophy. Like, the complexity of a flagellar motor implies many things about the origin of life. And I'm not going to answer that in this video, but it raises questions that people are debating, and they're talking about, how can this be? It's so complex. And well, you don't understand the time involved with how this came. All this is fascinating. So I just wanted to see it. So to get to the bottom of how this thing is, I decided to go to the researchers that made the image, which is a guy at Vanderbilt University. So today on Smarter Every Day, I did this about a month ago, just got in the car, drove to Vanderbilt, and we're gonna learn about a flagellar motor. Let's go get smarter every day. So I bobbed and weaved my way across the Vanderbilt University campus till I got to the School of Pharmacology and connected with Prashant Singh. Yeah, doing well. Nice to meet you. How are you? Yeah. Prashant is a senior research associate at the Iverson Laboratory at Vanderbilt. Just to give us whole context here, you have written a paper with your team in Nature, what's the?
Microbiology.
Nature Microbiology.
Yes.
And it's about a motor.
Yes.
That's made of molecules.
Yes.
That's on bacteria.
Yes.
Okay, well, can you show me where on a bacteria the motor is?
Sure. So if you see on the screen here, this is how a bacteria looks like. And the bacteria has two membranes. These two membranes protects the bacteria from getting disrupted. Or
So we're talking about the outer shell of the bacteria.
Outer shell of the bacteria.
Okay.
So if you see here, there will be two membranes, the orange and the blue. Now zoom into that.
Okay, so it's almost like a submarine. Forgive me, Prashant. I'm going to say a bunch of engineering terms because I'm an engineer.
I understand.
So it feels like a submarine with the outer hull and then the inner pressure hull.
That's correct. My dad was a submariner, so.
Was he really?
Yeah, he was an Indian Navy submarine, so for 20 years, 15 years, yeah.
So this bacteria in my head is kind of like a submarine.
Yes.
Okay, and is this the propeller of the submarine?
That is correct. This is the propeller or the flagella. Now this submarine does not have a rudder. It doesn't have a rudder, but it uses a propeller to turn as well as swim. So what we see here, the two membranes that are here, and there's proton filled in here.
Did you say protons?
Yeah, it's filled with protons, hydrogen ions in here. And it's
hydrogen ions, okay.
Yeah, so there are hydrogen ions in here filled, and on the inside here, there's very little hydrogen ion. So there's a gradient.
Forgive me, so
Yeah.
we have to go slow for me. When you say proton, you're meaning an atom that is lacking an electron.
Yes, just a proton, it's a hydrogen ion.
Okay.
So this is high concentration of protons in this region,
Okay.
and low concentration of proton in the inside of the bacteria.
Okay.
So now protons, every time there's a gradient, for example, there's a dam, water is up there, and there's less water, there's a gradient, energy can be generated, or it could be used, that potential energy could be used to kinetic energy and generate.
So there's a potential difference of electrochemical force of some sort.
Yes.
Okay.
So that's the gradient that this motor uses to turn itself. So what happens is, if you see here, this flagella, which is the propeller, is connected to a motor system.
How does it know when to turn the motor on?
There are sensors on the outside of the bacteria. So once it knows that there's a threat or there is more energy near me, it senses that it gets a chemical signal, and there's a cascade of signals that go through, and one of the protein well known for this is called QI, CHE and Y, capital Y, QI. So the moment it senses that I need to run away from this location or I want to go to a different location, that protein comes and binds to it, and it encourages the motor to turn in clockwise direction.
Okay, so we need to talk about what you just said,
Yeah.
because you just created a coordinate system inside the bacteria.
And the bacteria, yeah.
You put sensors on the outside of the bacteria.
Well, it already exists. Yeah.
Okay, there are sensors on the outside of the bacteria.
Yeah.
Somehow the bacteria knows where a sensor is triggered, and it knows how to trigger what motor on what side of the bacteria.
Yes, and to how to turn it.
And which direction to turn it?
Which direction? So that particular protein will make it go in clockwise. So this is clockwise direction.
Okay.
When it is not attached to it, it will go in counterclockwise. So the default motion is counterclockwise. When the motor turns counterclockwise,
You say counterclockwise from which direction?
from this direction.
From the tail,
outside.
the
yeah.
outside. Okay.
Yeah. So counterclockwise would be this.
Okay.
And when the motor is running in counterclockwise, the bacteria will swim forward. So like it's just the boat goes straight.
And that has to do with the shape of if I were to design this,
Yeah.
I would say that would have to do with the shape of the impeller. So the tail?
Yes. The way the flagella is made is like a whip. So when it starts rotating, it thrusts, the force goes backwards and it moves it forward.
Okay.
Now, you would think that it would also do the same thing when it's going in the opposite direction, right?
Yeah.
Now, what happens is when it's going in the counterclockwise, there are multiple flagellas on the bacteria body. All of them start forming a bundle.
Yeah.
And multiple propellers form into like one big propeller and pushes this straight, and it goes boom, straight. Now, when it has to it senses like there's a danger, I need to stop, I need to reanalyze my situation gradient, I need to test, I need my sensors on and test it again. It turns clockwise. When it does that, the bundle opens up. And when they open up, it just pauses the whole bacteria, and the bacteria starts tumbling all around.
Starts floating.
60 degree.
Yeah.
And
It no longer has a certain, there's got to be a word Latin in here, taxis.
Yeah, chemotaxis. we call it.
Chemotaxis.
Yes, exactly.
Okay.
So we call this whole process of bacteria's mobility like chemotaxis. It's a chemical signal that allows the bacteria to taxis or move from one place to another.
Okay.
Everything happens in like milliseconds, and there are some videos that show like bacteria moving from one place to another, and it's just like crashing. It's a biased random walk, and researchers have done this experiment. There's a petri dish, and
Yeah.
they put food in the center and put bacteria on the edges
Yeah.
of it, and you would think the bacteria would go straight to the food, but no, it just goes a little bit straight, then
Yeah.
turns around and goes in the wrong direction, realizes, oh, I'm in the wrong direction, goes back. So that we, as a person, you think random.
I'm getting emotional now
Yeah.
because there's a missile that I've worked on in the past, and it has what we call pulse width modulation control. And so what we do is we take the fins on the side of the missile and we dither them. We go like that.
Uh-huh.
And then all we do is we bias the dithering up or down. We go,
Whoa.
so it's constantly moving, but we just bias it just a little bit in order to make a movement. And so what took us a long time
Yeah.
to figure out, you're just describing it. This molecule or this bacteria has an operating system.
Yeah.
It has sensors.
Yeah.
It has effectors. It has
Yes,
actuators.
exactly, yeah.
And it has feedback.
Yeah, it has
and
feedback.
I'm getting emotional.
I know,
But
it's-
because it's so, it's a neat design, is what I'll say.
It is. And over the years, this design has like evolved to be so perfect. It just takes some time, but it does go where it's supposed to go.
Okay.
It doesn't have eyes like we do. It figures out by sensing and moving in directions.
It's an emergent behavior based on a few inputs.
Yes.
Emergent behavior?
Yeah,
Okay.
that's a good term.
So the structure of this motor, is it well known in the community? Like in all of research, people know about this?
They have seen a low resolution structure. So basically, if I blur this up, they have known that for like 15, 20 years. They have known it looks like this blob There's a ring at the bottom, there's a ring on the top, but what we have is a high resolution structure, meaning we can see each and every amino acid.
So I noticed on your video,
Yes.
it's almost like a big gear and a small gear.
Yes, that small gear is MOT-AB. That is what the proton comes through, and that's what turns this thing.
Prosh explained that the MOT-AB, the little part that spins like an ion pump, is able to interact with this band of red called Fly-G, and that has the ability to pivot 180 degrees, which enables the motor to change directions. So in your animation, you have one small gear going in. Is it literally one small gear, or are there many all around?
There can be, it can employ more if it needs more torque. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, up to 11 is what we see can fit on there, but maybe 12 or 13 as well. But we don't know exact number, how many can be employed. But it is a sequential increase depending on the load of the flagella.
Okay, so I'm going to get all engineering with you
Yes.
now. So if you have a torque,
Yeah.
you have to have a thing to react against.
Yes.
So that little pinion, I'll call it,
Yeah.
the little, what did you call it?
MOT-AB.
MOT-AB?
MOT-AB.
MOT-AB.
Yeah.
So MOT-AB is this little thing that's driving it.
Yes.
Is it pinned to the sidewall or something? What is
Yes,
it?
it's also in this inner membrane. So it's right here. So there's multiple colors that you see: orange, cream, and green. This all is one MOT-AB.
Okay.
And it takes protons or hydrogen ions from the top and goes into the low gradient here. And as it's doing it, it makes interaction with this red protein here, and this rotates, and it causes the motor to rotate.
Okay, but it's kind of pinned in that wall.
Yes, it is pinned in this membrane, but it can go round and it can shift a little bit in and out. MOT-AB is only turning in one direction. It cannot go in two directions. Here, the energy is only going from top to bottom. So how does this motor go in two directions? And that does because the MOT-AB, first it's outside, but when it has to go in the other direction, the red protein turns 180 degree, pulls the MOT-AB with it, and then MOT-AB keeps doing what it's doing, it's turning in the same way, but that causes the motor to go in the other direction.
It's like shifting into reverse in a manual transmission car.
Yeah. It's like almost like bacteria has a reverse gear. Reminds me of my motor that my grandfather worked on, where there's like copper coils that he's putting in these old, rebuilding these motors and putting fresh copper coils, and like it reminds me of that kind of structure.
Because your grandfather was an electrical engineer, right?
Electrical engineer. He used to build and rebuild motors for factories.
Is it fun to know that you're working on motors now, just like your grandfather?
Yes, it is. It's very. It feels very rewarding to be working on something that my grandfather worked in the past. Obviously, not the same scale, not the same thing, but just to know that I'm working on motors is fun. It's rewarding.
Okay, this is incredible. I love this. And we're going to come back and talk to Prosh later to understand how he got these images of the motor. But to get more context, let's go over and talk to Dr. Tina Iverson, who runs this lab. She's the PI, or the principal investigator. This is Dr. Iverson, and this is your lab, right?
This is my lab.
So congratulations on getting this published. That's a big deal. And simply put, what have you found here?
So we are looking at really this nuts and bolts of how bacteria can move, how they can move toward something that attracts them, like a food source, and how they can move away from something that would kill them, like an antibiotic. Bacteria are moving toward a food source as driven by their metabolism.
Okay.
And metabolism is like the foods that you eat. It's how you bring in energy into your body. But we're asking that question at a larger level, not just for bacteria, but for human cells. How does metabolism affect what our cells do in a way that dictates their cell fate? And so we were trying to understand, just at a general level, why does metabolism change what cells do?
I feel like every time we as humans have the ability to see smaller or farther, we make big discoveries.
Yeah.
Do you feel that?
Oh yeah, and I think that one of the ways the entire field is going now is, there's been this ability to image very small things with fine detail, but sort of medium and larger things in the cell with more blob-like characteristics. And some of the new technologies are now getting to these larger assemblies of proteins at finer details.
So we're seeing the overall system.
Yes. So before we were putting the system together from component parts, and now we're seeing the system more and more intact. And these bridges between the molecules at an individual level, which can tell us a lot about how they work, but molecules together working in concert tells us much, much more.
So we've got this motor that for the first time we can see an image down to the protein level. The question is, how do we get that image? How is Prash able to see this motor and understand its component parts in a way we haven't been able to understand previously? To answer this question, Prash took me over to the imaging lab where they use a series of cryo-electron microscopes to look at the structures to understand how they work. He introduced me to Miriam and Scott, who were kind enough to show me around. So now we're with Scott and Miriam, and these are the imaging experts. Am I saying that correctly?
Sure.
Yeah.
Okay. Yeah, does that work?
Absolutely. So all of our sample goes onto a grid that's right here.
So if
it's a mesh work on there.
Yeah.
What's it made out of?
Copper. So they can be made out of copper, gold. There's some other materials that we use for other very niche purposes.
Yeah.
But most of them are copper.
You have whatever sample you have that's in a buffer. It will get plunge frozen. You literally just drop your sample into liquid ethane and it just gets flash frozen. So your sample is in vitreous ice.
We're just making a network that can hold little tiny sheets of ice with protein trapped in it.
So that's what you start off with, and then after plunging, then we load it into that little cartridge.
Our middle room here is our Glacius microscope, so we'll walk in and look at it. So this is the Glacius. This is our screening microscope.
So this is like a quick look.
Just quick look. We have a source at the top that transmits an electron beam all the way through the column, and we put our sample in the middle and a detector at the bottom.
So you're shooting through it.
We're shooting transmission. We were going all the way through that sample.
The process that the scientists use to get these images is incredible, and I'm going to take a crack at explaining it with a super sophisticated animation style. So behold markers and paper. All right, so there's two types of bacteria at work here. You've got Salmonella and E. coli. Now Salmonella, that's where the flagellum motor is located. That's these little yellow things back here. So that's the flagellum and that's the little motor. E. coli, a different bacteria, has a little factory in it that can make things if you tell it what to do. So this process is called transformation. So basically, I just took that motor off, and I'm not going to put the motor itself into the factory in E. coli. I'm going to put the instructions of how to make the motor into E. coli. E. coli is not the only type of cell that has a little factory like this, but this is the one that the scientists chose to 3D print this particular motor. This is called transformation. This little factory goes to work, right? It makes a bunch of these little motors, and then you have a bacterial cell that has all these little protein structures in it. The act of creating this is called expression. We are now going to take all of these motors and do this process called purification. We're going to pop this, and we're going to use this grid, and we're going to basically dump all of the stuff that's been purified onto this grid array. We're going to flash freeze it, and then after that, we're going to use this really fancy 200 kVA microscope, and we're going to go through and we're going to look at the grid. Now, when we look at the grid, we're going to screen these. So this is kind of like a coarse view of what we're doing. We're going to go through and we're going to say, hey, look, there's one right there. That's important. Over here, oh, that's important. And then you're going to go all the way through this whole grid, looking and see which one has motors in it. How many motors does it have? It might be a lot. You're then going to move it over to the big microscope, the 300 kVA microscope, and that's where we're really going to take our close-up images. So what they do is they zoom in, and then they're going to take 50 frames of each individual little motor. The reason they have to do that is because at this level, you're down at the angstrom type level, like the atomic level. Things shake a little bit down at that level. So you have to take 50 images in order to compile that together. You have to make sure you take out that dithering. So at that point, you then have an image of a structure. Now that structure at that point, it could be like this, it could be like this, it could be at any number of different aspects, and Prash is going to tell us what he does with that information. Before we talk to Prash, if you want to learn more about microscopy and how the scientists do all this, I've got way more information over on a video on the second channel, which is Smarter Everyday 2. Go check that out if you want to learn more about this. So you get the images from the microscope.
So when you get the images from the microscope, they look somewhat like this.
And I can see the little crown looking thing there. Is that the bottom of a motor?
Yeah, this is the bottom. This is the top view. So I would say that this is how it looks. This motor right here is the view of this one.
Okay.
And then there is this view right here is a side view, like something like this.
Okay.
So we click on all of these particles, meaning we pick those proteins by hand and using the computer. We run a program of 2D classification, meaning we run a program where all these particles that has been picked so far are similar looking particles are put together into classes. And what we see here is some are just junks and some are actually our protein complexes.
So you go through there and you pick the ones that are the good stuff.
Yes, exactly. So this looks like a good stuff. This is a good complex. This is good, but these are not. So we don't select those, but select the good particles and put them together into a program for 3D modeling now. So we have 2D classes.
Yeah.
Once we have 2D classes, we put them together here to get a 3D version. So
so you build a 3D model, like you make these shapes actually match up.
Yes, each of those classes on pictures that we saw, we start matching them up as to which one is the top view, which is the side view, and program starts matching those up, and it does a very good job at doing that.
So it's really the ability to replicate so many that's the secret sauce. You have the transformation, putting that information into E. coli to replicate, and then E. coli expresses it. That's expression and then purification. So transformation, expression, purification, that's how you get it done.
Once we get the 3D model, it looks something like this. We can see all sides, and now what we see is a low resolution model. We try to collect all the good signals and remove all the bad signals and try to come up with a high resolution structure. So what you see here is an 8 angstrom, and from here 8 angstrom to 4 angstrom, it took us about 2 weeks to get there, 2 to 3 weeks.
You're removing bad data to get to the high resolution.
Get to the high resolution.
And then once you get to the high resolution, then you actually start drawing and mapping the proteins.
Yes, exactly. To get this map, we are trying to put the pieces in, the puzzle pieces in, and try to find what protein, what amino acid goes in which place. So since we know the sequence of the protein, we have the pieces, we just have to fit it in this electron density.
So we have these 2D images that we wrapped together using software into a 3D model. And at this point, we know it's made up of proteins, which are made up of amino acids. And so the question I had is, how do you know what chemical is where? And it's my understanding that biochemists are just smart, and they know that certain amino acids are shaped in certain ways, like physical shapes. So it's like a puzzle piece, and they just know what they look like. So they're like, oh, here's blobophil, or here's quadriline. I don't know these words, but they can like physically put the puzzle pieces in on the computer, and they can figure out what the structure looks like, which is incredible.
So if you see this curve, there's a curve here.
The coil,
The coil, and that's alpha helix. This coil, now we know alpha helix, only certain amino acids make in a certain orientation or sequence would make that coil.
Yeah.
So these prior information helps us trace this puzzle. So if you see now, we can fill these gaps with these proteins.
And this is a shape, a biochemist person would not be intimidated by this shape.
No, that's very common. It's commonly found in almost every protein, or not every protein, but like 90%, 95%.
It's intimidating to me. It looks like a bunch of squiggles. And, but this is normal.
This is normal.
So this is easily interpretable data.
Yes, it is.
Did you map these by hand and then just turn the image on? Is that what just happened? Or did you tell the computer to find the shape?
No, we mapped this, or previous researchers have mapped this in the past. We used the information as like, oh, this has been, they have done part of this. So let's use that and see if that fits in here. If it does, it's good. If not, we go in and do it by hand.
Wow.
So yeah, it can be doing one at a time. It can take weeks to months sometimes, depending on how big your protein is.
But you like it?
Oh yes, this is the best part. This is where like we get answers. This is what we have been like doing all the work for. Even when we're driving here, we are so excited, like what will I find today? So like now we come back and sit down, drink our coffee, and we're like, oh, so for example, I can go here and be like, let me see if there's any bonds being formed. So I go turn on the distances and angles. So there's a definite interaction between this and this. Maybe that is what's stabilizing this complex so well. They're forming some kind of bond between two amino acids. So this is what gets us excited, that we have found the interaction that are happening in this complex, what stabilizes this. And if we disrupt this, this can disrupt the motor. This can disrupt the connection it's having or interaction it is having with other proteins.
So once you disrupt this motor, if you could destroy the motor, or if you could stabilize it, whatever.
Yes.
Just if you had control,
Yes.
then you could start to do things that would affect the chemotaxis.
Yes, bacterial chemotaxis.
Bacterial, you could disrupt the ability for the thing to move where it wants to go.
Yeah, exactly. Like for infection, stopping the bacteria is almost like having an antibiotic, but not with an antibiotic. Because bacteria can get resistant to antibiotics. This is one of the many other options that people.
Maybe you get to invent a new word. Instead of an antibiotic, it's a lethargibiotic. You get to slow them down.
I like that.
Thank you very much.
Thank you so much.
So the flagellar motor exists, and it's amazing. It's complex, and it reminds me of an electric motor, and I love it. Like, I love this thing, and I think it's incredible. There are implications for the fact that something so complex exists and is so integral to the creation of human life. I mean, this is fascinating stuff. So it also opens up a huge debate. People say, well, how can something this complex come to be out of nothing? The logic goes like this. If this motor system is composed of complex individual parts, and all these parts work together to perform the overall function of rotating, then how did the individual parts come to be? Did it all have to happen at the same time? Or is there some evolutionary advantage to the cell for every intermediate stage of development? Is 15% of this motor advantageous to the cell? What function would 50% of the structure perform? What were the steps these components took to assemble into such a complex molecular machine in the first place? Scientists are trying to figure this out, and I encourage you to read their papers. Many seem to be focusing on the type 3 secretion system, which works like a hypodermic needle that a cell can use to inject other things. This device looks similar, but it's quite different in its protein structure. The complexity and origin of the bacterial flagellar motor is a really interesting conundrum. As I was a younger man and I would read things on the internet, I would find people saying, hey, you gotta believe all this over here. Or people would say, hey, you gotta believe all this over here. There's a big war going on. It's between science and faith, and you're either in one camp or the other. Get your flag and figure out where you're gonna put your flag. And the more I have matured and started to not really care about defending where my flag is, the more I've been able to learn from people no matter where they are. And I'm still working on this. There's a really interesting book that I'm reading. I can't speak for everything in the book. I'm not done with it. It's called Where the Conflict Really Lies. And it talks about this interplay between science, religion, naturalism. It's very interesting. It goes more into the areas of philosophy. And I love it because it challenges me and it's fantastic. So this is what I would encourage you. If you have your flag in a camp somewhere, I would encourage you to not defend a flag. I would encourage you to look at a flagellar motor and just think about it and think about how it is and what it be. It's a fantastic thing to think about. How did this get here? You have intelligence and you get to make up your mind. And I love that about consciousness. I love that about life. And so for me, the flagellar motor makes me happy. I feel joy. You know how when you go outside at night and you look up at the stars and you see all these stars and you feel small and you feel wonder? That's what this makes me feel like, even though it is small. I feel awe and reverence toward this thing. And as a Christian, this makes me want to thank God that it exists. I feel compelled with gratitude that this thing is so awesome. So that's just where I'm at. But what I would encourage you to do is just think critically. You have a brain. Don't defend a flag. Just think about how things are. And I hope you are very happy and experience the same joy I feel about this, no matter what you think about it. So anyway, enough about that. I want to say thank you to everybody that supports Smarter Every Day on Patreon. You'll notice there's not a sponsor on this video. I just wanted to make this for you, and I just want to say thank you to everybody that supports at patreon.com/smartereveryday. You're smart. You know what I'm doing. I'm just going around asking questions, and that's all these videos are. So this is the 300th episode. So thank you for supporting Smarter Every Day to allow me to do this so long. And I would encourage you, if you're interested, I would ask to consider supporting at patreon.com/smartereveryday to let me keep doing it. And if that's not your thing, totally cool with it because I'm having fun, and I'm grateful to all of you. Thank you for watching. I am Destin. You're getting smarter every day. If you'd like to learn more about the deep detail of all this stuff, I'll have a video on the second channel that goes into more discussions about how all this works, but I love it. Big thanks to everybody at Vanderbilt for helping me make this video. I'm Destin. You're getting smarter every day. Have a good one.